Well, let's get started. This is a talk, a sharing, if you will, by two students from Wayzata High School in Plymouth, Minnesota. And it came to us, and I thought, this is refreshing to get a student perspective on math modeling. These two students have excelled in mathematics, and I'm sure in other things. They participated in outreaches with mathematics, and we're looking forward to getting their perspective during the next hour and having some conversations with them about differential equations and modeling in particular. So Adhvaith and Bhanu, will you please take over?
Sounds good. Thank you so much, Dr. Winkle. We really appreciate the chance to be here, and thank you so much to everyone who's here at our presentation. My name is Adhvaith Sridhar.
My name is Bhanu Narra.
And we're really excited to present a wide variety view of math modeling. The first thing we wanted to talk about was creating a math model and how our perspective has helped us develop a 5-step workflow for developing any math model. And then we'll go through a couple of examples that we've applied these steps to and show how math models can be applied to a variety of scientific and real-life situations. The first step in any math model development is to identify the problem. So setting simple, achievable goals is one of the most important steps, because you have to break down this goal into smaller components that you can then model with simple math and add on more complex layers as you go. And so with any model, the first thing that Bhanu and I look for when developing is quantification. So we want our model to be easy to read. We want it to output a number or a small series of numbers, and we want to be able to compare this output with other potential outputs in order to tell the story of what the model is saying. And so to do this, we break down our goal into smaller components. And with any math model, we have some type of goal that we want to achieve, whether it be helping in the decision-making process or helping understand some natural process. And so breaking this down into a binary skeleton, as we like to call it, can help a lot. And so the binary skeleton gets named from the fact that our models typically take on a binary nature. So we either have variables that contribute towards an increased output or variables that contribute towards a lower or more negative output, and hence the name binary. And the skeleton part comes from the fact that we have numerous components that we string together, and the positive components are added together. The negative components are subtracted from those positive components. And this gives us a skeleton from which we can work with to make a more complex and more accurate model. So the next step is to gather data for each mini component of the model. And using reputable sources and data banks like past research, we map the data and read the story that the data tells. So we look at previously existing data to understand what our model should look like. And then we plug this previously existing data into each mini component and tweak it. We add parameters and operators so that each component tells the story it's supposed to tell. We use basic math functions in this step and add complexity with differential equations as we need to. And so the role of differential equations in math modeling is pretty important here, because primarily we have addition, multiplication, subtraction, and division as our functions to work with. But as we get into differential equations, we have a lot more flexibility and a lot more opportunity to quantify any event and make it accurately represented through math. And so that's what we kind of do here. And we tune the functions that we've built. We tune each individual component in order to increase the precision until we have a set of pretty accurate parts of our math model. So at this point, we combine each part of the skeleton into the final model. And something that's very important to consider here is scale. So oftentimes, different components of the math model will be on different orders of magnitude. So some components might provide a value towards the final output that's on the order of 10 to the fifth, 10 to the fifths. But others might be on the order of 10 to the negative 5. And so we want each component to have an equal weightage. And so we scale each component to be on an equal order of magnitude. So they all have an equal contribution and there's no skewed output. However, sometimes there are situations where we want to have some components be more important in the final output than others. And that's where we add weightage factors, which are just variables that serve as coefficients to each term in our math model. And these variables are determined by the user of the math model. And so this allows for the user to customize the model and personalize it so that when they're implementing it into a real life situation, they can prioritize certain factors over others in order to make the model more applicable to their individual situation. The fourth step is to test. So we verify the model with pre-existing data again at this point, make sure that it's precise, accurate, and telling the story that the data says. And then we run a sensitivity analysis. So a sensitivity analysis is simply using test data that's on the extreme ends of the range. And so we use extremely skewed input data, and sometimes this can be unrealistic or unlikely to occur. But the reason we do this is so that we can determine the upper and lower limits of the model, and we can determine the range of values for which our model can actually give you an accurate output. And this prevents people from using the model in situations where it might not be as helpful. And it can also tell us when we need to revisit the model and tweak it so that it still works at these upper and lower extreme limits. The final step is to present and share the model in a coherent way. So we want to explain our reasoning with a logical train of thought. We want to be thorough so that people who want to learn more about our thinking can truly understand what we did and can potentially find parts that we could improve. So we always, stay open-minded and ready to revisit and revise the model when necessary. So that's the fifth step of the math modeling process. And now I'll hand it off to Bhanu, who will run through a couple of examples that we've done and show how these steps can be implemented in two types of situations.
Mm-hmm. Yeah, as Adhvaith said, there were kind of like two main situations where we applied this 5-step process. So for the first one, it was kind of more of a real life application, whereas the second was a little bit more of like a scientific research application. So for our first example, we'll be looking at if someone were to purchase a solar panel system and they wanted to know what kind of battery system is the best accompaniment for the solar panel, how can they do this? Because it's not at all obvious, and there's a lot of very complicated factors that go into determining which is the best battery system. And so if we could make a model to help homeowners discover which is the best system, it can make it a lot easier for people to start transitioning into solar power. So for our step one, we decided to identify a bunch of variables that would probably go into this calculation. So first of all, we had a bunch of variables that contribute to the battery. So for example, the instantaneous and continuous power, as well as the storage of the batteries. This is, for example, like how much power the battery can let out over a certain period of time, and how much storage it has in total. And we also wanted to know how much energy is produced by the solar panel. And so all these factors would make sense to contribute in some way to which battery system is optimal. So for example, if someone uses a lot of energy, they need a lot more batteries, or they need a battery with a lot higher ratings than someone who has a lot less electronics. So another factor that we thought was important was the lifetime and the price of the battery, because obviously the battery isn't infinite, it's going to run out at some point, and then it needs to be replaced. And so taking into account both the lifetime and the price can get us a more accurate estimate for the price. And another important factor was surface area, because obviously batteries aren't just these little things, they take up a big space. So making sure that we minimize the amount of space in the house that's being taken up by a battery is also another factor that we thought would be important. So again, we would start by defining some good terms and some bad terms. So we figured that the more energy that you get and the more storage that you have, the better. And so that would be a positive term. Longer lifetime is obviously also a positive term because that means that would reduce cost in the long term. And price and surface area, obviously those are negative because the more surface area that you take up in the house, the less you have for other availabilities. So our idea for this system was basically the homeowner would just come and input a bunch of data. So they would like go through and see what devices are they using, how much energy do they use, how much energy is coming from their solar panel system. And essentially after all this is inputted, the system would go through all the battery systems that we implemented into it, and it would determine which would be the best one. So for the data for this, we decided to go with 5 different systems that are available. And so these are all the data for the systems. As you can see, some of them are very cheap compared to other ones. But if we look at some of the other ratings, like the instantaneous power or the continuous power, they're really bad compared to the other ones. And so you need to buy a lot more of those ones to get the same effect as the other ones. And so this would lead to a lot of complications for someone who wants to buy a battery system because it's not immediately clear whether it's worth investing in one really expensive battery or many small batteries. And so our system is designed to help make this easier for the user. So after we went through the process of dividing the complicated steps into a bunch of individual parts, we were able to look at each individual part in more detail. So the first 2 terms are basically just how much energy is produced by the battery. And so we were able to take this kind of, this really simple idea about the energy, and we were able to get a more precise notion of what the function would look like. And so we got something like this, which essentially just determines how much power is produced by the battery and how much energy is used by the devices in the home. And so the third term corresponds to area. And again, we changed the functional form so that if for example, you don't want a house completely filled with battery, that would be completely ridiculous. And so we decided to make a term that would explode essentially as the battery surface area increased over the surface area of the house. And so this is what we would expect because obviously someone can't buy a battery system that completely overruns their house. And thus we wouldn't even consider a battery system that would require that. And the last term takes into account both price and lifetime. And also it's designed to have a similar order of magnitude to the other ones. So something you might have noticed is that there's a bunch of like Greek letters in front of everything. And those were the weights that we were talking about earlier. So having weights, if a homeowner is particularly wealthy and they can easily afford a more expensive battery system, they could tweak that weight and make it less. And someone for whom money is scarce can increase that term so that it's more important. So we ran the system through a bunch of different tests. So first of all, we just inputted like the average American household data. So like how much energy they use and how much money they have for a budget. And so the AES 7.4 kilowatt hour system was the recommended for the average American household, as well as for an off the grid home, which perhaps has less space available and uses less energy. So the AES 7.4 kilowatt hour one is more like a mid-range device. So we also decided to test some extreme situations. This was the sensitivity test that Adhvaith was talking about earlier. So for a smaller house that has less money available, we tweaked the weights accordingly and inputted the data. And so the best system that came up was the Tesla Powerwall Plus. And so this system, it has a really high storage and it's kind of expensive, but you only need very few batteries to actually run everything you need. And it'll also take up a lot less space than the other batteries because you need to get a bunch of the cheaper batteries in order to accommodate for the price of the other one. So another sensitivity test that we ran was for a huge house that has lots of money. And so in this case, we expected to get the highest quality, best battery system. And that's exactly what happened. We got the Electric Power Pod 2 Plus, which is just the best in every way, except in price because it's very expensive. So when we tweaked this price term, all the other terms worked in order to make this one the best system. And finally, we needed to make it easier for like someone who wanted to actually convert to solar power to convert and actually use this model. And so we decided to make a pretty simple app interface that we designed. And so the homeowner could just go in and put in all the data, like the budget and the surface area and how much energy they use. And then the system would essentially just give out which battery system is the best, how much it would cost, how much area it would take up, and also it would rank all the battery systems. And so having a system like this, having an app like this, would make it a lot easier for someone who wants to convert to solar energy to actually do so. So that was kind of our first more like practical application of modeling. But sometimes we just have interesting questions that we want to ask, and math modeling can be very useful there as well. So in this case, we learned that some birds like plucking hair from live animals to insulate their nests. And it's not at all clear why they would take this risk. And so we decided to make a model to see if we could predict which birds would take the risk and which wouldn't. So again, we started splitting up the risk into different parts. So we figured that temperature would play a role if the bird needs insulation for the nest. We also considered sources of hair and predators because that would make it more dangerous for the bird to try to go get hair from these animals. We also looked at some alternative sources. So for example, if there's a lot of trees and vegetable insulation options, vegetative insulation options, it's not clear why the bird would instead go to an animal. And so we decided that that would be a factor. And also another thing was innate insulation. So if a chick has a lot of feathers, it doesn't necessarily need as much external insulation from the nest. And so in this case, our model was a lot simpler. We just defined a cost function, B minus R, with B being the benefits and R being the hindrances. And so if the function was positive, then the bird could, it's probably worthwhile for the bird to practice Kleptotrichy. But if it was negative, then it's not worth the bird taking this risk. And so we decided that having more sources was a positive term, having more predators and vegetations or alternative sources, and having more innate insulation, those were all negatives because those just make it so that it's not at all worth risking your life for animal hair. So for just a quick aside, in the previous slide, we mentioned all the other terms other than temperature for positives and negatives. And that's because temperature is slightly more complicated. So looking at the data, we found that as the temperature decreased a lot, the insulation value of the hair became less and less important because like penguins, for example, they don't build nests and they also have a lot of innate insulation. And so it's not clear why they would even risk their life plucking hair. And so we figured there would be some golden temperature range, or which we call TP, where it would be most likely for the bird to pluck its hair. And we said that basically the farther the temperature gets from this TP, the more negative that this function will get. So this would also be part of our benefits function, such that like it'll essentially be an upside down parabola that'll peak exactly at the golden temperature. And so we expect that when the temperature is there, it'll obviously help the function increase. And so after we solved the differential equation and we put in a bunch of boundary conditions on it. So for example, we wanted it such that if the temperature was the temperature of the chick, it wouldn't necessarily be as important to have insulation. And so after we plugged in all these boundary conditions into the differential equation, we ended up with this final function k of t. And so in the cost function, we would get also add a weight beta to it, and that would also have a positive term. So for collecting our data for this term, we decided to try to quantify some of the other terms that are a little ambiguous. So for example, the goodness of a source of hair doesn't make too much sense initially. The danger of a predator also is kind of hard to define. And also we needed a bunch of data about which birds actually use, which birds actually practice Kleptotrichy. So we just decided to make a simple system where we defined a hair quality index for different animals, which is essentially just determined by the length of the hair and the insulation depending on the color. So for example, closeness to black. Something that's hair that's more black offers better insulation than hair that's lighter. And so based on this, we were able to deduce a bunch of different qualities indices for different animals. And another thing that we need to consider was how dangerous different predators were. So for example, predators that naturally hunt birds are, we decided to add a factor of 10 to how important it is. And we also decided that having more attacking devices and having more mass is also more dangerous to a bird. So then with all this consideration, our final model looks like this. Again, it looks very complicated, but we broke it down into simple steps and we decided which sort of functional forms each term would take. And so again, the first two terms just correspond to how much hair is available and what temperature it is. And the last couple terms just correspond to alternative sources, predators, and innate insulation. So then our weights, we were chose to match our data, like with the big Excel sheet that had a bunch of data about the birds. And so we were able to tweak this model to be more precise. And so we were finally able to test our model with this example of the tufted titmouse. And this bird lives in a moderately dense forest. And there's also a lot of predators in this area, but they're not very dangerous predators. And they also have a lot of deer to choose from. And deer are obviously not predators to them, so they're not at all dangerous. And they're also the most common source of hair for Kleptotrichy. Also, the chicks have a low innate insulation. And so with all these different factors, we expect the bird to practice Kleptotrichy by our model, since we got a C-value greater than 0. And that actually lines up with the bird's behavior because it does practice Kleptotrichy. So for presenting and sharing this, we made a pretty simplistic one. We just made a presentation and a YouTube video. And we were able to get a lot of feedback from experts in the field about a bunch of factors that we missed and some factors that we considered that really weren't as relevant. For example, a sleeping predator is not at all dangerous like an awake one, as we looked in the previous image. It's actually plucking hair from a fox in that case. And so with all this information, we were able to consider which terms we would change and which ones we would add next time. So with that, I think Adhvaith will now discuss how math modeling can be more useful in education.
Yeah, thank you, Bhanu. So now I'll be talking about how experiences like ours can be really helpful when incorporated into a high school educational curriculum. So our experiences with math modeling typically fall under 3 categories. The first, arguably one of the largest, is competitions. And so there are a variety of competitions that are available for high schoolers and even some middle schoolers to participate in and get involved and acquainted with the math modeling process. And so a notable one is the Simio challenge using differential equations modeling, the Scudum math modeling challenge. And so that's actually the challenge that inspired our solution to the Kleptotrichy, the Kleptotrichy question that Bhanu just presented. Another notable competition is the COMAP challenge. They actually have 2 sub-challenges, the high school mathematical contest in modeling and the interdisciplinary contest in modeling. And both of those are 2 levels of competitions for high schoolers and even undergraduate students to participate in the math modeling process. And the COMAP actually inspired our solution to the solar panel problem. That was where we got that problem from. And then another important competition is the MathWorks Math Modeling Challenge, also known as the M3C Challenge. And something important to note about these challenges is that they vary in structure. While some of these challenges take place over a week and competitors can spend as much time as they would like over that week to develop their solution, others like the M3C challenge take place over a 12-hour span. So it's like a sprint of 12 hours where you just continuously work on your model. So these different structures definitely hold different merits and they teach you different skills. The second main way that we've engaged with math modeling is through presentations and outreach, like our presentation here, where we show ways that teachers can implement math modeling to high schools and help other students also get the benefits of math modeling and have the same or similar experiences that Bhanu and I have had. And finally, we can also work with professional math modelers and learn from them. And so I'll briefly touch on the applicability for high schoolers, and math modeling is definitely very helpful to implement into a high school curriculum. And it's never too early or too late to start math modeling. It's applicable to numerous situations and can help improve decision-making processes for important decisions, as well as improve analytical thinking skills. And finally, practicing math modeling from a young age can help prepare you for the future. So it can help equip a new generation better prepared for making important decisions, such as the switch to renewable energy that Bhanu discussed previously.
Another thing that I'd like to briefly mention is, for example, there's a lot of scientific discoveries like for COVID-19 and looking at the projections for case numbers and such. Those can be very difficult for like the general public to understand. Like if the case numbers are going down, but the rate of infection is going up, it can be hard to actually understand why more precautions should be taken. And so understanding like differential equations and mathematical modeling for these situations can help get a faster public response and one that's more equipped scientifically.
Well,
Yep. And our final remarks are just about technology and math modeling. So math modeling is an ever-growing field, and the future is here. It's about using computers and code to expedite the math modeling process. And common modeling softwares include Python and MATLAB, which enable greater computational power, provide graphing opportunities, and a lot more freedom with how we develop our math models and how accurate they can get. And so that's another facet of math modeling that's growing and is important to explore, beginning even from the high school stage. So yeah, thank you so much for attending. We appreciate everyone here for taking the time out of your day to join us on our introduction of math modeling. Thank you.
well, thank you too, very, very, very much. I'm sure that all of the college professors who are listening are going to be contacting your admissions office first thing Monday morning and saying, get these two students to our college with a full scholarship. But I'm sure you're going to have lots of choices throughout your life. You've obviously mastered quite a bit and have the maturity to reflect on it, to organize it, and as you said in your steps, to communicate it very well. I thank you very much. And I would applaud you and suggest that we keep in touch. And if people want to get in touch with you, they can contact you through the high school, or you could put your email in the chat, or they can write to me and I would forward that. But wonderful, wonderful presentation. And I can't wait till you become a professor or a senior lead engineer and guide others. Terrific. Thank you.